let's finish this chapter. So, the last thing here is an alternative method for determining the enthalpy of a reaction using standard heats of formation. Essentially what this does is it takes values from a table and we use those values to work out what the enthalpy change for a reaction is. Those values that come from the table are the aforementioned heats of formation. And what a heat of formation is it's the enthalpy associated with the construction of 1 mole of a substance from its elemental components. So actually what we've seen mostly in the last couple examples with Hess's law would be examples of a heat of formation. So like this, for example, here with propane. This is how do you make propane from its free elements, carbon and hydrogen. Well, that's it. So this is actually the heat of formation for propane. Same thing here with CO2, same thing with water. It is just make those molecules from their elemental constituents. What's the enthalpy change as a result of that? That is the heat of formation. And so these standard heats of formation is really, truthfully, kind of just doing Hess's law, but it doesn't look like it's Hess's law. It's kind of an easier, faster way of doing Hess's law. So the way this works is we have a whole bunch of different molecules in a table, and in your book, I forget what the appendix number is, but it's in an appendix. I want to say it's appendix J, but I could be remembering that incorrectly. But you can find the appendix at the back of the book. I unfortunately do not have a copy in front of me right now, but I have a different book with the same values. And it just has a whole bunch of different molecules, and it has delta H naught values. So it looks something like this. Delta H of formation with a little O sign up there. We're not going to worry about what that means right now. In Chem 2 we'll talk about what that means. But we're going to use those numbers from the table to determine the enthalpy change for a reaction by taking the values for the products of the reaction, multiplying them by the coefficient from the balanced chemical equation, adding all those together, and then subtracting the values for the reactants times their coefficients, added all together. So it is the sum of the products minus the sum of the reactants. So the values from the table will look something like this. This is a very small appendix here. This is just a figure actually from a book that we used to use. The appendix at the back of the book that you will use is a lot more detailed than this. These are just some of the more common ones that you'll come across. So let's look at an example here. We're going to find delta H of this reaction. So what we're going to do is we are going to take the products, add them all together, and subtract from that the reactants, add it all together. So these are going to be our products. These are our reactants. So if we look at our products, we have 3 CO2. So I'm going to go ahead and put in a 3 there, because I know whatever number I get for CO2 from the table, I'm going to multiply by 3. So if I go and look at my table here and find CO2 in the gas phase, there it is. It is negative 393.5. And I'm going to go ahead and leave it unitless, but everything here is in kilojoules per mole. But that mole unit is going to go away because what we're multiplying with the coefficient is actually the number of moles. It's how many moles are reacting. So the moles is actually going to go away because of that coefficient. So that's the CO2. I'm going to add to that the number for water. So I have 4 of whatever the number is for water. Water is usually listed under oxygen on these tables. So water in the liquid phase, because the phase does matter, is at negative 285.8. And again, that's kilojoules per mole, but just for the sake of space, I'm going to not have a unit there. The reactants, so that's these, I have propane, so I'm going to go back to the carbon on the list here, and I only have one of this, but I'm going to go ahead and put the 1 in. So let's see here, where is propane? Well, there it is. C3H8 is negative 103.85. And then the oxygen, which I have 5 of, if you look that up on the table, what you'll find is it is 0. Because if you have something that is already in its elemental form, there is no heat of formation for that, because it doesn't need to be formed. It is already in its elemental form. So it is 0. All right, so we have our values here. All we have to do is add them together. So we have 3 times negative 393.5 plus 4 times negative 285.8. That gives me a total of negative 2,323.7 for the products. So then I'm going to take that number and subtract from it negative 103.85, which gives me negative 2,220, essentially, kilojoules. Which, if you notice, this is the same reaction that we looked at back here. And I know I don't have the numbers up here anymore, but we had 2,200, I think, is negative 2,200 is what we got for this answer. The reason why it's just a little bit different is probably because they were done at different temperatures. The enthalpy values do vary a little bit based on the temperature at which the reaction is occurring. So that's most likely the reason for the slight difference. But they're very, very close to one another. Percentage-wise, it's within 1%. Okay. For this next one here, why don't you pause the video and give this one a shot yourself. See if you can look up the numbers in the table at the back of the book. Again, products minus reactants. And then unpause when you get that done, and we'll work through it together. So once again here, we're going to do products minus reactants. We have CO2. That was negative 393.5. If you notice, most of the stuff here is the same as the previous reaction. There's really only one thing that's different. The number of things that are reacting are also different. So we have 1 CO2 instead of 3. So we have 1 times negative 393.5 plus 2 times negative 285.8. So those are our products. And we're going to subtract from that the reactants. Now we have methane instead of propane, so I will have to look up that number. So methane is negative 74.6. We have one of those. By the way, if these numbers are a little bit different in the book that you're using, like I said, I have a different book here. Don't worry about that. They'll be close enough for sure. Especially like for the homework, there is a there's some leeway essentially, where as long as you're within, I believe it's 5%, then it still counts it as being correct. And the values won't be off so much, they would be off that much. All right, so we have negative 74.6, and then just like before, oxygen is 0. And so if we add all that up, negative 393.5 plus 2 times negative 285.8 minus negative 74.6. That leaves us with delta H for this reaction is negative 890.5 kilojoules. All right, I hope that's what you got. I hope I did the math correct. It's one thing I always worry about making these videos. If this was in a classroom, when I make math mistakes, usually there'll be a student that pipes up and says, I didn't get that. And then I realize, oops, I made a mistake. So I apologize if I had a mistake up to this point and I didn't catch it. Sometimes I catch it myself. All right, last one here. Why don't you give this one a shot as well? So why don't you pause the video and try to work out delta H for this reaction, again, using the numbers from the appendix. All right. So just like before, products minus reactants. So our first product is nitrogen monoxide. I'm going to flip over here to nitrogen in my table. And NO is positive 91.3. And I have 4 of those. Just like before, all of these are in kilojoules per mole. I'm going to add to that 6 times the number for gaseous water. Notice that it is in the gas phase now, so we cannot use the same number that we used from the previous question, because that was in the liquid phase. So let me see. Where is my oxygen? There it is. So water in the gas phase is negative 241.8. So those are my products, which are those. So then we're going to subtract the reactants. So I have 4 ammonias. So going back to the nitrogen here. Ammonia in the gas phase, specifically, is negative 45.9. And again, I have 4 of those. And I'm going to add to that 5 times the number for O2, which is still just 0. All right. So, if I add those together, 4 times 91.3 plus 6 times negative 241.8 minus 4 times negative 45.9 gives me delta H for this reaction is negative 902 kilojoules. Okay. I hope you got that answer, or something very, very close to it. If maybe one of the numbers was a little bit off from one appendix to another, there is sometimes some disagreement on what those numbers should be precisely, but they're all very close to each other. Just a quick note of caution on these problems. By far the most common mistake I see is people forgetting to do products minus reactants and just writing down the molecules in the order that they're shown in the reaction. So instead of having products here and reactants here, where you're essentially swapping them, their location left and right, students will kind of get in the groove and think, and kind of not think about it, and they will accidentally do reactants minus products. So don't fall into that trap. Products minus reactants always, and you should be fine. So that is it for this chapter. Good luck on the homework, and I look forward to talking to you next time.